this is everybody's first definite integral. So I will show you guys how to do it a very classic way. Alright, so I'll show you. Firstly, you keep the limit as n goes to infinity, and notice everybody has the 1 over n, so I'm going to factor that out. In the meantime though, n square, everybody also has n square on the bottom as well, right? So I'm also going to factor that out right here. And you will notice that this right here will just have 1 square left. Next, we will have 2 square left, and then 3 square left, and then so on, up to the very last part, which is n squared, like so. Okay? Then you are going to see this is actually just very nice to be n approaching infinity. This is 1 over n to the third power, and all this n times n plus 1 times 2n plus 1 all over 6. Does this look familiar? You should. The limit is something to approach infinity, right? So this is the limit as n goes to infinity. On the bottom we have 6n cubed. On the top, just for fun, I'm going to multiply out for you guys. Here we have n squared plus n, and then we multiply 2n plus 1. So this right here is 2n to the third power, and then n squared, and then 2n squared. Yes, together is 3n squared, and lastly we have n. Right? You really don't have to multiply out everything, but number 21. My soul is loading deep in my body. Limit is n approaching infinity. This is everybody's favorite calculus question. On the top, we care about 2n to the third power. On the bottom, we also have the same thing, n to the third power. They cancel out, reduce 2 and 6, we get 1/3. Hey, the answer is just 1/3. Very, very nice. Very, very nice. Alright? Now it's about time to tell you guys what this represents. This, as I said, is everybody's first integral question, and it's just going to be the area under x squared from 0 to 1. How? Well, I'm going to show you. Don't worry. When we have 0 to 1, the idea is that we are going to cut this into n equal width rectangles. That's why we have all the 1 over n. So just imagine we cut into n equal piece rectangles. So this is the first piece. And I'm going to use the right end point to construct the rectangle. Meaning that use this x value, go up, hit the curve, and then we are going to just construct our rectangle right here. And because we have n rectangles, just imagine a 10. Then in this case it would be like 1 over 10, right? But again, it's n. So this right here is 1 over n. What's the height of this rectangle? It's just a y value. We use this x value, 1 over n, we put it here, and we get 1 over n squared. So this height is 1 over n squared times the base is 1 over n. So this right here is the area of the first rectangle. Next, well, we have this rectangle here, but it go up by another 1 over n. So this x value is 2 over n. So go up, hit the curve, and then construct the rectangle. The width is still 1 over n though, but the height, we put 2 over n into the x, so we get 2 over n squared. So this right here represents the area of the second rectangle. So on, and the very last one is 1, which is just the same as n over n. We go up, hit the curve, and then we construct our rectangle. Yeah, width is still 1 over n, the height is n over n squared, the area of the last rectangle. As we have n approaches infinity, each rectangle is going to be so thin, like infinitesimal small. Yeah, so you can actually get the area. Okay. Alright, so that's cool, but I want to show you guys what's cooler. Check this out. This right here It's just a way to say we have the limit as n goes to infinity. And then you see that we have all the addition, which is the summation, which we can use sigma for it. We can write it as sigma, like this. And then you see we have the 1, 2, 3 up to n. They changes, right? They change, right? So that's where we need to use the running index. We'll say I, just the running index. I goes from 1 to n. Inside here, we have I over n, yeah? And then we square that, and then we multiply by 1 over n. I just put a 1 over at the end. This right here is the width, aka delta x. Delta x, another way to look at it is from where to where, and we write it as b minus a over n. So the range, right, it's only 1 unit away. If we start with 0, we end up with 1. If we start with 17, we end up at 18. So that's the structure, and guess what? If you know the structure of this, we can change this to a super version. That is the so-called integral. What's the function? You see, the input is I over n. That's what we talk about. We enter all this into the x. So that's the function. So the function in this case is x squared. Yeah. And then you can actually look at it from here, 1 over n, right? And based on this, we know b minus a is 1. So just go ahead and start with 0. You can always start with 0. You will see it in another question later on. So we can just go from 0 to 1. And then the delta x, that's so, I don't know. It's 2022 already. Don't write delta x, write dx. So anyway, this right here is the explanation of the integral notation. Right? So you can ignore that. I want you guys to be able to go from here to here. But of course, it's hard sometimes. So definitely draw the picture and convince you guys that all the setup is correct. It's correct though, because you see we just want the area going from 0 to 1 under x squared, and the dx is just the width of the rectangle. So it does make sense when we have the dx in the integral notation, right? So how do we do integrals? Well, we are going to use the reverse power rule. So if you haven't learned about the integrals by now, you can watch my 100 integrals video, or you can pause for a little bit. For now, if you are in Calc 1, then this is what you have to focus on, and maybe come back after a week or two, then this is what you will be doing. Anyway, we use the reverse power rule, meaning that we find the antiderivative, add 1 to the power, which is 3, and then divided by the new power, so we have 1/3. So an antiderivative for that is just 1 over 3 x to the third power. And then we're going to plug in. Plugging 1 and then subtract plugging 0. This process is called the fundamental theorem of calculus part 2. Anyway, I'll show you. 1 over 3, 1 to the third power. This is the first part, minus plugging 0, we have 1 over 3, 0, third power. This is 0, this is, yes, you know it, 1/3. So yeah, this weird curve shape has the area of a very nice number, 1/3. Right? So keep in mind of how we go from here to here. But I want to warn you guys though, a lot of times the questions will put 1 over to here. So you will see we have the limit as n goes to infinity, and then 1 over n, and then the sigma, and then I goes from 1 to infinity, and then whatever this is. Right? But just worry about this right here will give you the function part. This right here will tell you from where to where, and then change that to the integral, and that's it. All right. So here we go. Let's combine this into a sigma notation. It will be the limit as n goes to infinity. Everybody has 1 over n. We can factor it, and then you see I'm going to put it right here. Okay. Usually nobody really put it at the end, but that's the dx part. You just have to realize that. And then we have the sum. I goes from 1 to n, and I is this 1 2, 3, 4, and so on up to n. That's the changing part. And this time, you see we have 2 plus I over n and then square. Okay, now, based on this, what region are we talking about? Well, again, let's focus on this right here first. We have 1 over n, huh? So this right here tells us b minus a will give us 1. If we start with 0, we end with 1. If we start with 25, we end up with 26, etc., etc. All right. Does that help? Not really. Okay, just start with 0. That helps. Just start with 0. That helps. Okay. Just start with 0. So I'm going to claim that this right here, it's actually just the integral going from 0 to 1. Just start with 0. And then the function is actually 2 plus this right here, I over n. It's just going to be the x. And then square, and then dx. So you can change that to an integral. This integral, of course, represents the following. Have a look. If you graph 2 plus x, it's just like, if you graph 2 plus x squared, it's just like you have a parabola, but you put to the left 2 units, right? So when x is negative 2 here, we have a parabola, something like this, okay? And I'm saying that the region that we want is from here to here, 0 to 1. And then have a look. This is y equals 2 plus x of, to the second power. Does this satisfy our original? It does. Have a look. We go from here to here, so the whole thing is 1, cut into n pieces, so each piece is 1 over n. So the first x value that we can use is 1 over n. Put it here. The height is what? 1 over n in here, so we have 2 plus 1 over n squared. The next x value, 2 over n. Put it here. We have 2 plus 2 over n squared, that's the height. And then everything here, the width is 1 over n. So, yeah, that should convince you guys, huh? Okay. What if you don't want to start with 0? I don't know. If you want to start with 2, it's okay too. Show you. If you start with 2, then you go up to 3 per our discussion earlier, right? And in that case, the function is no longer the same right here, but you put it as just x squared dx. Why? Let me show you. This right here will give you that as well. Check this out. So we have our x squared. Horrible picture, I know, I'm sorry. But if we go from 2 to 3, so this is the region that we are talking about now, okay? Why? We start with 2, because this right here is a 2. Check this out. From here to here, the whole thing is still 1, cut into n pieces. So this right here, the width is still 1 over n. So we still have 1 over n there. Good. But what's the x value? From here to here is 2. We have to add 1 over n. So this x value is 2 plus 1 over n. And then you see our function is x squared. We are going to put this whole thing, 2 plus 1 over n, to here, and then go up. You see, that's how we can get the height, which is that. Same thing. Next, this right here is what? From here to here is 2. 1 over n, another 1 over n, so altogether is 2 plus 2 over n. Whoa, look at that. This is the x value. Put it here. Look at that. Same thing. So that's why, as I said, just always start with 0 for this kind of questions. Everybody will be so much happier. If you don't want to start with 0, that's totally okay. It's just that you kind of move the region around. This is a microphone. I moved to here. That's still the microphone. Same thing. So it doesn't matter how you move it. horizontally, you will still have the same area under the curve. This right here is definitely easier to compute though, so that's the advantage compared to that. Alright? So I'm going to compute this for you guys. Do the same thing, antiderivative, so you get 1/3 x to the third power, and then we plug in 2, 3, this right here, 1/3, 3 to the third power, that's the first part, and then minus 1/3, 2 to the third power, yeah, okay, that's 27. Minus 9. 18? No, that's 8. Oh my goodness. 27 minus 8. 19, right? 27 minus 8 is 8. This is 19 over 3. There we go. Almost got it right. I was like, oh, how can this be so nice to be like 3? Not possible. Cool. Now, put this in the sigma summation form. Here we have the limit as n goes to infinity. Everybody has 3 over n, so let's write it right here. Sigma I goes from 1 to n. I want to see 1, 2, 3, 4 all the way to n. So you do this. This is the same as 3 times 1. This is the same as 3 times 2. So on, so on, so on. And here we have 3 times n. Right? So that's the part that's changing. So we have 3i over n and then square. So the question can be presented this way or this way. So be careful with both ways. And here's the important point. You see the 3 and 3 match. It's crucial. You'll see. But anyway though, let's do what we did earlier. 3 over n. This 3 tells us b minus a is equal to 3. So if we start with 5, we go to 8. If we start with 0, which you should always start with 0, you go to 3. So here's the deal. Integral 0 to 3. Perfect. Now, what's the function? We have a 3 right here that's bothering us. Is the function 3x squared? Or are we having just like 0 to 3, x squared dx? Which one? The answer is this right here. Not that, this right here. Why? Because the reason that we have a 3 right here is because the whole thing is 3 and we cut into n pieces. So that's why. And I'm going to perhaps just erase this, and I'm going to just give you guys a picture right here real quick. So you see, when we have x to the some power, but it's actually just x to the third power. But no, kidding, just kidding. X to the second power. Because we're going from 0 to 3, right? So each width is 3 over n. The next one is 6 over n. So you see, that's why I said 3 and 3 match. So you see, you put this to the x value, we get that for the height. You put this to be the x value, in here, you get the height. So the function is actually just x squared. It's not 3x squared. Be really careful with that. So it's x squared dx. Work that out. 1/3 x to the third power, 0 to 3. Put 3 in here. 3 to the third power is 27. Divided by 3 is 9. And then subtract, plug in 0, just 0. So yeah, we're good. So that's number 20. Alright, let's put this in the sigma summation first, which is just the limit as n goes to infinity, 1 over n. All this can be put it as the summation. I goes from 1 to n. 1 pi, 2 pi, 3 pi, so on, so on, so on, up to n pi. So we are talking about sine of, let's put it as I pi or pi I pi over n. Okay. Now, this number is just 1. And that so means b minus a is equal to 1. So, This right here is equal to what? Integral going from 0 to 1 only. Now the hard part is, what's the function? Is it sine of x or sine of pi x? The answer is sine of pi x. If this is a 1, this pi will just be the coefficient, and look at the I over n, which is, that'll give you the x. I'll convince you guys that this actually is legit. Sine of pi over x. Let's just say it looks like this, somewhat like that. Hopefully this is legit. If not, I will have to correct it. I'm tired, so we'll see. So you see, we have sine of pi x. So this is the curve, and the deal is that we are going from 0 to 1. When x is 1, sine of pi is 0, so we do have this part right here. Okay, we want to have, oh, the picture is wrong. Let me try to draw it slightly more realistic. Because this is 0, let's say this is 1, and when x is 1 over 2, you get 1, so when x is 1 over 2, you get sine of pi over 2, which is 1. Doesn't matter. Trust the computation, all that stuff. Anyway, going from 0 to 1, this right here is 1 over n, 2 over n, 3 over n, and so on. Put this into this x, pi over n. Put this into here, 2 pi over n, and so on, so on, so on. Okay? Yeah. So, I want to see how many of you guys are still I want to see how many of you guys are still watching this. Question for you guys. What if today we have the limit as n goes to infinity? What if we have a pi here and over n, and the summation I goes from 1 to n, and then sine of I pi over n? So tell me what the function is, and tell me from where to where. I'll give you guys the dx there. Right. Do not just put the pi at the front and just say, hey, that's the answer, multiply by pi. Don't do that. Don't do that. Do the things I said. That's better that way. So the range will be going from 0 to pi. Okay, the range will be going from 0 to pi. And then tell me what the function is. But anyway though, what's the answer for this? Alright, I'll show you guys how to do this. Antiderivative of sine is negative cosine, because the derivative negative cosine is positive sine, and then the input is pi x. But we will have to divide by this constant here. How do we do all the antiderivative of that? I have 100 integrals already. By the way, trust me, this right here is the answer for that. Yes, now put a 1, put a 0. So here, be really careful though. 1 over pi, negative 1 over pi, cosine of pi times 1. That's the first part. Minus, put a 0, so we have negative 1 over pi, cosine of pi times 0. Okay. Cosine of pi is negative 1. Cosine of 0, that's pi times 0, 0 is 1. So here, this right here gives us positive 1 over pi. And then negative negative becomes a positive 1 over pi. Wow, this was crazy. The answer for that is 2 over pi. How pretty is this? Whoa. So how to do this? First thing first. 3, right? B minus A is 3. Just start with 0, yeah? 0 to 3. And this right here will give you the function. What's the function though? 3 and 3 match, so you pick the whole thing to be the x. So just square root of 1 plus x. Just like that. This picture is like this. Okay? And then we go from 0 to 3. okay? But the truth is, we can move it to the right 1 unit, and that will give us the integral going from 1 to 4. And then you can see that it's just like this. It's the same area, okay? And we can just look at the square root of x. Much easier to integrate, because now we can look at this as integral x to the 1/2 power dx 1 to 4, and then just do the antiderivative that I showed you, add 1 to the power, which is 3/2, divided by the new power, which is 2 over 3, and this right here is 2 over 3, x to the 3 over 2, and then plugging, yeah? Putting the 4, and then putting the 1, putting the 1, okay, 4 to the 3 over 2 is, you take the square root of 4 first, and then you do the third power, which is 2 to the third power, which is 8. So it's 8 times that, which is 16 over 3. This is 1, so it's minus 2 over 3. So all in all, 14 over 3. It's almost like pi, but the other way around, huh? Okay. Ready? Cool. It's 1 over n, so just integral going from 0 to 1. Here, this is 1, this is 2, so the function is e to the 2x. Okay. Integrate this, e to the 2x stays, but divided by 2, because that's the derivative of 2x. And then just plug in numbers, 0 and 1. Be really careful with when you plug in zeros. Sometimes it does matter, so don't ignore it. So here we have 1/2 e to the 2 times 1. And then minus, plugging 0, 1/2 e to the 2 times 0. Okay, this is just 1 over 2 e squared, and this is just 1, so just minus 1/2. Done. 97. Okay. Limit as n goes to infinity, and then we have pi over 4n sum I goes from 1 to n, and then secant square pi I over 4n, pi over 4 match. This means we go from 0 to pi over 4, and the input is just what? Secant square x dx. Okay? Yeah. Very different. Very different. Okay, and now let's just work this out. Derivative what function will give us secant square? The answer is tangent. So tangent x, 0 pi over 4. Plugging pi over 4, tangent of pi over 4 is 1. Plugging 0, tangent of 0 is 0. So all in all, the answer is just 1. So nice. Yeah, so I'm just going to write it right here, because I want to fit another question here. Number 98. Number 98. Okay. Here's the limit as n goes to infinity. And then we have 1 over n, sigma I goes from 1 to n. And then we have cosine. This is crazy. It's just I over n. Wow. How do we do this? Well, same idea. Integral 0 to 1, because it's still 1, yeah? 1 over n match. So this is just cosine x dx. Okay? Yeah, and then let's just go ahead. Integrate this, derivative what function will give us cosine? The answer for that is just sine x. Positive though. Plugging 1, sine of 1, it's a number, it's legit, just leave it. It's not like a special value, you cannot really simplify it, so just sine of 1. Plugging 0, sine of 0 is 0, so the answer is just sine of 1. Right here, let's divide this by n squared. and of course do the same on the top. Divide this by n squared and do the same right here. And divide this by n squared, do the same, and then divide this by n squared, and then do the same. What good does this do? Let's see. Check this out. If we have n over n squared on the top, everybody has a 1 over n now. Perfect. Let's factor that out. Put it here. And then sum I goes from 1 to n. Alright. And then let's see. Now, because I put that over there already, so we have a 1 on the top, and over this over that is just 1. And 1 squared over n squared, as we said earlier, that's exactly what we want, huh? That's plus parentheses I over n squared. This is 2 squared over n squared. This is 3 squared over n squared, so on, so on, so on. Good. Alright. 1 over n and then 1 I over n, right? So this is good. This becomes the integral going from 0 to 1. The function is 1 over 1 plus x squared dx. Integrating this, we get inverse tangent because the derivative inverse tangent is 1 over 1 plus x squared, and then we plug in. Plugging 1 in here, inverse tangent of 1 is pi over 4. Plugging 0 is 0, so this right here is it. Maybe we can just divide the top and bottom by n, just like what we did earlier. Yes, or you can just factor out the n from the bottom. So it depends on how you like to look at it. Perhaps let's divide everybody by n. It's more consistent than what we did earlier, so let's do that. Perfect. So here is the limit as n goes to infinity. And then we have our 2 over n. Let's put that right here. Sum I goes from 1 to n. And then now on the top is just 1. And then we have 1, right? And then I'm going to write it as plus, and we have, this is like 2i, yeah? 2i over an integral going from 0 to 2. And then the function is 1 over 1 plus, is x or 2x? X. Match, right? So x. Okay, dx. Integrating this is ln of 1 plus x. We don't need the absolute value because everything is positive. Ladies and gentlemen, plugging 2, we get ln 3. Plugging 0, ln 1 is 0. Final answer, ln 3. 100 limits. There you have it.